So I was having trouble with this question here, and I wanted to solve it. So I asked my friend Matthew Ngai for help to solve it. So, hello, Matthew Ngai.
Yo, what's up?
Thank
That's my
you.
theme song. No copyright, please.
Okay, so the question is two masses, m1 equals 3.0 kilograms and m2 equals 1.0 kilograms, are attached to an inextensible string of negligible mass over a frictionless pulley as shown below. If the m1 slides along the ramp at a constant speed of 0.20 meters per second after m2 is released, what is the coefficient of kinetic friction between m1 and the ramp? So the first thing we should do, and the easiest because we'll need it, is to find the weight of m1 and m2. So I'll calculate that right here.
And meanwhile, I will draw the forces acting on the two weights or masses.
Thank you, Matthew. So
No
let's
problem.
start with uh, m2. Let's call it fg2. So that would be mass times gravity. That would be the weight of it. M2, if we look in the question, it is 1.0 kilograms. So 1.0 kg times 9.81 meters per second squared. So that would just be 9.81 newtons, but to 2 sig figs. Let's keep all the digits though. Let's underline that. And now we can find the gravity of the, or the weight of the second, or M1. So let's do that right underneath. FG1 equals M1 times gravity. So that's 3.0 kg times 9.81 meters per second squared. And if you put that in your calculator, 3 times 9.81, that's 29.43. Newtons to 2 sig figs. So now that we have the weight of the two, we can go to solving the problem. So what we're looking for is the coefficient of friction. So the formula for that is F equals mu k times Fn, and we're looking for the coefficient of friction of m1. So we need to find Fn, which is right here, and Ff. And let's look back at the question. M1 is sliding along the ramp at a constant speed of 0.20 meters per second. Constant speed means the forces are at equilibrium. So all the forces have to cancel out. That's important. And we don't, this is kind of like a trick question. We don't even need this 0.2 meters per second. Don't let that confuse you. So now, let's just focus on, let's try to get rid of the M2. So what this pulley means, this is probably the confusing part of the question. It just means that this string is pulling M1 with a force of the weight of m2. So it's just making a vector in the direction up the ramp of 9.81 newtons. For some reason Matthew didn't put that vector there,
Sorry, what?
but he can learn from his mistakes. So
Wait, what am I supposed to do? What?
you forgot the
Tension?
oh, you put it down here, but
Yeah.
okay, whatever. So imagine this arrow, it's pulling on the M1. So
Yeah. Yep.
let's
That's what
just
I meant to do.
let's just draw a free body diagram here. So this is the force that M2 is pulling at. So that's the tension in the string that's pulling M1 up. And then there is the normal force, which is perpendicular to the plane. And then there is gravity, which is just straight down. And then there's also FF, but we can't tell which direction FF is in yet, because FF has to be in the opposite direction of where M1 is traveling. So, but we don't know if it's sliding up the ramp or down the ramp yet. So we can just put that in later. So first we should split FG, which is this one, or let's say FG1, into its components.
Diagram sucks. Oh, keep going.
What was that?
Nothing.
Okay.
You know, mine's all colorful and stuff, but yeah, keep
Okay,
going.
yeah, let's just look at Matthew's for now. So
Okay, thank you.
you see FG right here, FG1. He split it into these two component vectors. One is going straight down, and it's the opposite of Fn, so it's equal. Those are the only two vectors that are perpendicular to the plane, so that means they must cancel out. And then there's also the x component of Fg, which is pulling the M1 down the ramp. So now let's try to find FGX and FGY. So to do that, I showed in my last video that this angle right here, the 28 degrees, is always equal to this angle inside the vector triangle. So now we can solve this. We know FG1, we can solve it using trigonometry, SOHCAHTOA. So we know that FG1 is 29.43 newtons. We know that the angle is 28 degrees. So we have the hypotenuse, and we're looking for, let's start with FGY, which is Fn. We're looking for the adjacent, so we'll have to use cosine to solve this. So cosine 28 equals adjacent over hypotenuse. So FGY, let's just call it Fn because they're the same, over hypotenuse, FG1, which is 29.43 newtons. And then just multiply the 29.43 over, then we have Fn equals, put that in your calculator, cosine of 28 times 29.43. And the 29.43 is 2 sig figs. So then we get 25.9851 to 2 sig figs newtons. This is important. That'll help us find our final answer. Now we find FGX. This one is a lot like the finding Fn, except we just used the sine function. Sine 28 equals opposite over hypotenuse, because it's sine. So FGX over FG1, which is 29.43. So FGX over 29.43 newtons. Then we have FGX equals sine 28 times 29.43. 13.8165 to 2 sig figs again. 165 newtons. Okay. So, oops. So now let's put this on our free body diagram. We have this, which is FGX. And then let's just write the value so I can show you something. It's 13.82 around. Let's just put that here. And then this one, which is the force of M2, is just 9.81. So from this, let's also put Fn here. Fn, and this one is also Fn, so they cancel out. And then we put down the components, so let's just erase Fg. And then now we can see that M1 is being pulled up the ramp at 9.81 newtons, but it's also being pulled down at 13.82 newtons. So what this means is that right now, how the vectors are, the mass would be accelerating down the ramp. But we know that's not true because it has a constant speed. So that means there's another force in this direction that is balancing out the 13.82. And that is the friction force, because it's going in the opposite direction of the motion. So finding friction force is pretty easy. We just know that, here, let me write it better. We know that what this is, FGX, equals to this one, M2G, which is the force of the string pulling on the mass, times, plus F. So now we can just put the values we have for these in here. Matthew, do you want to put them in for me?
Yes, sir. I would love to. Alright. So you have FGX. Notice how my handwriting is much nicer.
Yeah, They don't care.
M2G. So M2G is, well, we calculated it over here, but I'm just gonna use the values so it's more accurate and you don't get rounding error. So M2 is not 3, I'm bad. M2 is 1 kg times 9.81 meters per second squared, and then plus F, and then, oh, FGX, we already solved that, sorry, my bad. So
It's okay.
we're gonna do FGX is over here, so we're gonna plug that in, so 13 point, wow, I'm being such a hypocrite, I literally just said we should do, wow, okay, whatever. 165 on the 13 equals 9.81, because it's just times 1 on the 8 newtons plus FF. So that means FF is just 13.8165 newtons with sig figs on the 3 minus 9.81 newtons on the 8. So then we find that FF is equal to 13.8165 minus 9.81, and that's 4.0065. And since the sig fig is on the ones place here and on the tens place here, we have to keep it to the ones place. So FF only has one sig fig. Morgan should have done a sig fig lesson, so if you don't understand that, blame him.
Okay. Well,
Alright,
now that we have those, we're going to be using this formula. So we just solved for FF, which is 4.0065 newtons equals mu k times Fn. And then, oh, yeah, I'll just put in, Matthew, you want to put that in?
yes, I would love
You,
to.
you, you look
I'll
pretty
just do
eager.
everything.
Okay,
I'll
thank
just
you.
do everything. Alright, so Fn, we found it over here. That is 25.9851. So we have 25.9851 newtons with a sig fig on the 5. So mu k will just be, when you divide 25.9851 newtons, and then 4 divided by 25.9851 newtons. So mu k, you'll find when you divide 4.0065 by 25.9851, you will get 0.154. And since 4 only has one sig fig, you only keep one sig fig, so your coefficient of friction is equal, of kinetic friction, is equal to 0.2.
Without
And
any
that's
units.
the answer. Yeah, with no units, because it's just a coefficient.
Yeah. Okay,
So,
so
yeah, as you can see in my genius diagram, I wrote the green is the driving force of the system, so it's what makes it go, and the red resists the system. So friction resists motion, and this M2 resists the pull of FGX. If you, yeah,
Fascinating.
colors are
Okay.
amazing.
Well, before we end it off, I just wanted to let you know that we haven't checked with Mr. Wang, so we're about 99% sure of this answer, but there is still a 1% chance we're wrong. So,
I'm never wrong. But
yeah,
okay,
yeah.
yes.
Yeah, let's just say we're not wrong.
Yep, yeah, we're definitely not wrong.
Okay. So thank you for joining me, Matthew. It
No
was fun
problem.
making a video with you.
Yep, same.
Make
It's like
sure
dinner time
to
now.
make sure to check out Matthew's YouTube channel.
Which is non-existent, but it will be coming very soon.
Oh,
And I'll be
well,
tutoring Fortnite.
well, well, I look
Cut that
forward to
out.
that, Matthew.
No, thank you. I don't
Okay,
play anymore.
thanks for watching. Bye.